All right, so I mentioned yesterday, which is probably off camera now, but whatever. I had the capacitor, and so when I go to charge, that little light bulb went on and slowly dimmed. So what happened?
Ran out of electrons.
So you can't put any more electrons into it.
It what?
You can't put any more electrons into it. Your capacity.
It flowed or it flewed into the capacitor until it completely charged up. And now it's completely charged up. And if anybody wanted to, oh boy, I could do that. Never thought about this one. And then if I go to discharge, click, that one comes on as it discharges out. And so now it's discharged. But we could go to discharge. And then who's brave?
Me.
Touch those together.
Well, you gotta face us, dude. You can't do it. You gotta see.
I can't see over here.
Yeah.
Oh, went through the light bulb.
Come on, dude. I
Damn
signed a
it.
waiver. Give me something good.
Can I touch the battery? Like,
Well, I guess this is how bad things happen. If we charged it up and then put the cables onto here and then touched or wait. I should turn the camera off. Okay, now touch those two screws.
A little spark.
It didn't do anything?
It's a tiny little spark, yeah.
Oh wow, that's sad.
What
Okay.
if I just did this one?
The cable gets really hot. I've done that. I would have thought that would have sparked real well. The little ones we use in for the magnetos, I actually what it is, I think the battery just doesn't charge it up enough. We have a magneto a machine that tests capacitors and coils you'll be seeing in use in the next few days. And we charge up the capacitors, but I believe it's 120 volt AC we're charging them with. And so they're very tiny, just that tall, well, that size of my thumb there. And you take the wire, bring it back around, you can hear it. Snap! So it'll get you. So I know it's fun to charge them up and just leave them laying around so somebody picks them up. Okay. Something I was thinking about that just bugged me is in my notes it talked about, it actually says, and I got this from something, that the peaks for three-phase were 120 degrees apart. I just kept thinking, that can't be right. It can't be right. Because like from this point right here to this point right here is 360. No, it's not. It's 180. Wait, from here. Oh, okay, that's what it is. Here to here is 180. That is 360. So divide that by 3. That would be 120. Okay. So yeah, it's 60. Well, no. Here, here, here. So that was right. So from here to here is 360. If we called this 0, this would be 90. This is
180.
180. This is 270. This is 360. Okay, so it's actually from here to here is 360. Oops, wait a minute. Right here is 360. Sorry, 360. This is getting a little crazy. All right, so got that 0, 90, 180, 270, 360. So this happens at 90. This one's happening at 180. So, and this one's happening at 270. So that makes them 90 degrees apart in a three-phase. So, all right. Didn't want that bad information out there. All right, so back to the fun stuff. We were talking about effective power yesterday. And now I'm in that spot where, okay, why is the...
So say the three-phase AC is 90 degrees apart on peaks?
Yes.
Are you sure? You said that
No.
yesterday. I don't think it is because 90, 90, and 90 are not 360.
Let's do it again.
There was one that you're starting at 0.
I just didn't like my notes. I don't know where I got it from. It's like... Okay, 0, 90. Okay, then we have to do the three phases. Which now I'm just drawing them. We could even look at it right here. How much is this?
90.
And this is
180.
180. So we could split it right here.
Yeah,
This
so
one
90.
started here and this one started here.
So
So,
180 divided by 3.
what do you get?
60.
60. So that'd be 60, which it makes sense. Times 2 is 120. So it's the peaks wouldn't be, it would be, I don't know. Just don't like that.
Yeah, because it's like that's making up one half of a
Yeah.
full.
So it bugged me when I said it was, when the notes, whatever I got it from, said 120.
At least in
The
that
way we were,
representation of it.
the way we were thinking it is, each of the, like, I mean, you're doing a full 360, so each of the little, each of the loops is gonna be 120 degrees apart.
Oh yeah, I even drew it out, and I figured out it was peaks are 60 degrees apart. So I don't know. It's not on the test, but each peak would have to be 60 degrees apart because we just did it down here. Now we do it up here, 90, 150. That makes it worse. Plus 60
That
would be.
makes, I kinda get that though.
Yeah, yeah, it's 60 degrees. Each one starts at 60. All right.
Is the peak value of the amplitude still 120?
What?
Is the amplitude peak value still 120?
No.
So
That's like saying, is the battery 4 volts? Right?
I obviously don't know.
Well, no, let's straighten this out. That would be like saying, is the battery 4 volts?
Okay.
If it's a 4 volt battery, it is. Is this battery 4 volts? This one's 12. So is the peak 120 volts? If it's a 120 volt system, it is. Right?
Okay.
So how high it goes up is how many volt system it is, in a way of speaking.
Amplitude is voltage.
Yes. Or amperage, if you're measuring amperage. So it's not a set value, it's whatever you want it to be, or whatever it happens to be. Right?
Okay. Yeah.
This was just for the sake of example.
Yeah.
Like actually measuring voltage or anything like that.
Right. Okay. What's that?
I was just teasing that one. In that example, each phase has more and more voltage than the other.
Yes. Thank you for that. All right. So let's maybe kind of revisit that then. So this is I'll make this my 0 line. Sometimes that straightens out. Okay. So that's,
Perfect.
thank you. Okay. Oh, it's because I have that. All right. There we go. There we go. Okay. So that's 0 volts. 0 volts right there. Got it? Okay. And so now I have AC, and it comes up to here, and it comes down to here, and it does this. And how many volts is it to right here?
1,000.
It
Whatever
doesn't
it
matter.
is.
There's X. There's
It's
no,
X. Okay, I like that. It's X. It's whatever I've either set the voltage generator for. What if I plug it in a oscilloscope into the wall over here? What is it coming out of the wall?
110.
Okay, that's going to be somewhere between 110 to 120 volts. That's just house voltage. It's just that. Go across the street, and we have 3-phase. We have 240. So it could be 240. We'll look at that in just a little more about that. So follow. And then we had, let me see, do I still have this up? Hey, look at that. All right, so, oh, I know what I want to do. Schematic. Let's just get rid of this because that's making life difficult. All right. There we go. We got the graph. How many volts is it to the peak? 1. It's just 1 volt right there. Why is it 1 volt?
You said it.
So that's what I set it to. So it's not 120. It's just 1. Okay. And what is it down here on the bottom? What am I measuring across not across the bottom, across the sides? What am I measuring? Time. So this is voltage. In this case, it's voltage. I could make it amps if I wanted to. No, but I didn't. All right. But back to power, effective power. All right. So effective power in DC. In DC, we figure power is just power, right? It's what?
Constant.
Constant. What's the formula?
PIE.
5.
Power equals
Okay, current times voltage. The problem with AC is the measured value only happens twice per cycle. So it maxes, then it drops to 0. Then it maxes, then it drops to 0. So it's this constant on-off, right? These are running off AC at 60 cycles per second. These are literally shutting off 60 times per second. We just can't perceive it, but it really is happening. So you think about how much brighter they would be if they were on all of the time. But they're not. They're shutting off constantly, building back up, shutting off, building back up. Although they're fluorescent, so that may have another thing. But anyway, so effective power. Therefore, so when we're thinking about power then on a resistor or something or anything else, the power that it's using is different than DC. Make sure I got the right pins going. What am I going to say now? So therefore, an average must be therefore an average must be, we'll say, calculated. So we have to calculate the average of this entire waveform that goes up and then back down. What is the average of that if you just calculate it out? If you assign if you assign each one, say 100 points around this way, and arbitrarily, you just picked a dot and went all the way around and said, okay, then I'll do 100 of those. Just went around here and said 1, 2, 3, 4, 5, 6, 7, 8. Ooh, that's how you get different pins. Okay, and I just made dots all the way around, and
Morse code.
yes, it is Morse code. It says help me, I'm drunk. And we went around, we added those up, and they all, of course, had a positive value, and it came to a positive 200, because it's an arbitrary number that I just made up. And then if I added all these up down here, it'd come to an arbitrary negative 200. So the average value is 0. So there is no power. Well, that wouldn't work. And you have to figure out that it's really only 0 right there, right there, and right there. So the rest of the time it's actually on. It just swings the other way. So there's this thing. Let me see. Well, I'll finish my notes here. So it must be calculated. But we have to kind of figure out we don't really cancel out the positive and negative to get 0. We actually get something. I don't like the way my notes are going. It's called RMS. And so I'll have to explain RMS when we get to RMS. Root mean squared is exactly what it is. So we're going to be talking about RMS values in just a little bit. So the average ends up being RMS, root mean square. Root mean square. Which is to say that we actually take all of the values, square them, so now they're all positive numbers, and we take the square root of that, we're going to get a number. We're going to circle back around to that. Let's see, effective value, say the effective value, let me see. The effective value of AC is that which produces the same heat value or same heat energy. Is that which produces So if we think about it, we could take a resistor, plug it into a DC battery, measure the heat coming off of it, and say, okay, now let's plug it into the wall. You get the same heat value, go, okay, that's how we figured it out. When the heat matches, then we kind of have the same power coming out. I would suggest that, let me see, maybe not yet. Yeah, I'm going to abbreviate some of this. You should, okay, what I was going to say, and I'll just say it. I would suggest you have another sheet of paper ready, handy, just one sheet that is called a formula page, because we're going to be doing a lot of formulas over the next few days. And that should not scare you. That should actually give you some comfort because all you have to do is follow the formulas and you'll be like, I don't know what I just did, but I did it. So another sheet, we're just going to write formulas. And then maybe off that sheet, we'll write another one. We'll put them all in order. So, all right, formula for power is...
You're right. You're right.
Power is... What's formula for power?
P equals IE.
P equals IE. Or I squared... I don't expect this to work. I got to go over here. P equals I times E, or power equals I squared R, or P equals E squared divided by R, which is just kind of PIE, but a little bit different. All right, I'm going to abbreviate some of this. See, therefore, the heat produced is proportional to the square of the current. Yeah, we don't need that. So to figure out the average AC power, we average the square values and then unsquare them. I already said that. Square root, which is called the RMS. And I had an example here, which I just crossed out because I was like, don't waste your time. What did I say? Yeah, because it is. Yeah. It just complicates things. So another way of saying this is all the instantaneous values of the sine wave are squared. The results are added together, then divided by the number of results to get an average, a mean. Follow? Which is what I said. The square root of this gives the effective voltage. This is called the RMS, root mean squared. Back on track. All right. Sure, 6. Why not? Root. Oops. I forgot again. I remember the days when I used to just write on the board and life was good and everything was easy, and I just went through like 8 pens a semester. So root mean square.
Nothing's stopping you.
You wouldn't like it. I did not mean it for it to be capitalized. It decided on its own. Root mean squared, or RMS. Root mean squared. That is this is the, I don't want to say this.
Seems the board's trying to tell you something, sir.
The board is?
Yeah. What else would it capitalize mean?
Mean.
When it's talking about you.
All right. What? Thanks.
That's a great way to get there.
Yeah, I know. What I want to say about root mean square, what is my definition of that? That is the effective voltage. Effective voltage of AC. Or SC. I mean, it doesn't matter to me. All right. So again, we have a sine wave. All right, and that sine wave is trying to tell me something. Just that. Oh, I know what happened. Oh, look at that! It made the little mustache thing. That was fun. Okay, 'cause I had the wrong pen yet again because I can't remember to switch pens. All right, we have a sine wave. This right here represents 0. Okay, so we have an amplitude, and it comes up to here, and I say this is 100 volts. Why is it 100?
That's what you said.
Because I made it up right now on the spot. Okay, so that's 100. So with an oscilloscope, we put it on there. We're going to see that sine wave go right up to 100. Just like with this one here, it went right up to 1. Okay, that is what you see on an oscilloscope. So the wave really is going all the way up to 1. If we plug it into the outlet over here, it really is going to go up to, we'll say 110. But if I take a Simpson meter and I put it on amps and I shove it in there, what happens?
You blow out and
I'll blow it up. All right, so you're just seeing if you're paying attention. So I take a Simpson meter and I plug it in there on volts for AC for at least 110 volts. I will not see 110. If I measured this circuit that I have right here built with a multimeter, it will not read 1. It will read RMS. So meters read in
720
R.
or something like that?
Nope, it reads RMS. So, all right. So, not love where my notes go. So, I'm just going to have to make up stuff. RMS effective is effective voltage of AC. Switch pins. Somebody's going to have to train me to do this. And so I will say meters read in RMS. And this will be our formulas for RMS. Formulas for RMS. All right, so trying to figure out how to actually write it with this technology so it's going to work out. It doesn't that great. Okay, so E effective. We'll just do it. E effective, EFF. So it'd be like E, the little effective. E effective equals 0.707 times E max. That is not working. I'm going to have to go over here. Formulas. All right.
And 0.707 is a fixed number.
Yes. E effective equals 0.707 times E max, which is like saying we have the outlet right here, or I don't know, what's easier for you? The one I had here with 1 volt? We'll use the thing I had here with 1 volt. So we had a sine wave with 1 volt. So what is my maximum?
1 volt.
1 volt. So 0.707 times 1 volt, the maximum, equals 0.707. So if I had 1 volt, what would my Simpson meter read?
0.707.
So I would look at it and go, well, wait a minute. I just set up for 1 volt. Now it says 0.707. Kelly, the meter's broken. Blew a fuse, right? We all clap. I go, calm down. It's supposed to say 707 because
It's the RMS.
meter reads an RMS. Okay, so we can do the same thing for I effective equals 0.707 times I max. Great place to see a movie, I heard. Which is simply just saying that it's going to do the same thing. Meter's going to read an RMS. Doesn't matter if it's on volts or it's on amps. It's going to read RMS, which is 0.707. And this is something I would want on my formulas page. Doing E effective is 707. And we could even go rewrite it. Maybe let's say the meter equals 0.707 times O-scope.
So
O-scope peak.
this is why
There.
we were saying like during 301 or rather 300 that voltmeters are basically the same, or not the same as ammeters, but they're like this. The functionality is the same between both of them, right?
I don't know. What?
You're basically saying like a voltmeter is an ammeter with higher resistance, right?
Yeah, that just confuses people though. Don't go there with that. All right, so you follow? What I'm saying here is the meter, this is the meter, the effective. What the meter is going to say is times 707 what the O-scope peak is, the oscilloscope peak is. All right, then we can turn it around. We could say, well, wait a minute. What if I measured it with the meter? How can I figure out what it says on the oscilloscope? So that is E max equals 1.414 times E effective, which is the same thing as saying the oscilloscope equals 1.414 times what the meter says. I think that kind of works.
So you multiply 1.414 by what you're reading on your meter,
Yep,
and then you get
Your peak.
you get the peak.
you get the peak.
So then you multiply 0.707 on what you read on your oscope to get your RMS.
Say it one more time.
Okay.
I wasn't
So you
listening.
measure on your oscope,
Yes?
and you multiply whatever the peak is by 0.707, and you get your RMS.
Yes.
Okay.
So for the root mean square, the definition we put effective voltage of AC. It could be effective amperage of AC.
Try it again.
You said for the RMS,
RMS.
definition, you put effective voltage of AC. So
Yeah.
it's effective amperage of AC
Yeah.
as well. Okay.
Yeah. Okay, I'm going to put a little asterisk by the meter, asterisk. Why asterisk? Well, I'm going to tell you that asterisk means that that is dependent upon frequency. May change due to frequency. In other words, some meters have frequency limitations. Once you start messing with the frequency, then they have an error that is induced within the meter. And so you have to go to the manual and you have to figure out what the error of the meter is. And I don't believe any of the newer modern digital meters have this problem. I think they're fine. I look it up in the book. I would. But I know the Simpson meter definitely has an entire page dedicated to, hey, if your frequency is this, then we're off by this much. This is analog. All right.
May change due to what? Sorry, I listened to it. I just wanted to.
I was having the same problem, trying to think and write.
It's hard to do sometimes.
Yeah, it is. Your Simpson meters, for sure, and I think most analog meters, have a problem with frequencies.
I know. Just go there now so I can. I want to see what you wrote down.
May change due to frequency.
May change due to frequency.
Yeah.
Okay, I understand.
But this is the formula. They're not going to say, well, if your frequency is this and it's 0.717, it just simply is, oh, it's going to be off by this percent. So,
Okay.
yeah. But that is the formula that we're going to stick with. So just remember, for practical purposes, when you are in lab and you're doing something, then if the frequency gets too high, you can expect that your meter is not going to read very well. This is a dangerous thing for me to say, but I will say it because it's not for all practical applications. The value value stated is in RMS unless otherwise stated. That statement is more like out in the world. That is not so much in the lab. Don't go, you didn't say. So, okay, in the lab, you have to read it in context, what we're talking about. Okay, so make sure in the lab it's in context in the rest of the world. So when we say we have 110 coming out of the wall, it is in. Are you sure?
That max.
What's that?
Should be max.
Is it RMS or is it peak? That's how we would distinguish. Peak would be oscilloscope or RMS would be a meter. So 110, peak or RMS? You guys don't sound very... Unless otherwise stated.
Because you said earlier that would read on a oscilloscope like that.
That is true. But unless otherwise stated, and what do we say? It's 110. Did we state anything? So unless otherwise stated, it is in
RMS.
So it is RMS. So what if I hooked it up to an oscilloscope? What would the peak voltage be?
155.54. Do that right?
All right, so if we have on our wall, oops, damn it, did it again. We have 120, say 120 volts. It's either 110 or 120. It's not like I don't know. It just kind of varies between that. So coming out of there, we say it's 120 volts. So what is the peak?
155.5.
Well, that was at 110. I just
Oh,
changed
sorry.
it.
169.68.
169.68 volt. So we have 120 volts is
RMS.
RMS. Peak is,
169.68 volts.
what is peak to peak?
Double that.
That would be 339.36.
Peak to peak is this times 2, which is
339.36.
339.36 volts. We got it? What if, I don't know what European is. I went someplace and a certain peak voltage, I had a peak of 56 volts. What is my RMS?
39.59 volts.
What'd you get?
39.59 volts.
39.59 or 6. So 39.59? 59 volts. That's my RMS. Everybody's following so far? Yes.
Actually, I'm kind of confused on how you're getting that. For the above one, I guess I'm confused on how you got the peak, which formula you used.
I'm sorry. For some reason, just a slight problem hearing
So it
tonight.
says 120 volts RMS, then you get the peak from that 120 volts.
Uh-huh.
And I'm confused on which formula you're using for that.
Thank you for asking. Okay, then that's kind of on me for going a little bit too fast. So to get the peak, it is RMS 120 volts times 1.414. Where did I get the 1.414? That is on our formula sheet.
Yep.
And that equaled 169.68 volts.
So if we're trying to go from peak to RMS, in that case, we'd use this 707.
You got it. So to get that, it is peak 56 times 0.707. Because remember, peak, now it's going to be less than peak. Let's see. Right here. So this right here is the peak. Then this right here, that's RMS. It's always going to be below the peak. So RMS / effective.
It's the average of voltage in the top with the time included, right?
Time is not included. Time has no function in this.
So it's just the average of the
Average of the peaks. And right there, the M stands for
Mean.
mean, which means
Average.
average. So that line right there represents the average, which is less than the peak, because we have some off periods and some lower periods. And if we want to go from RMS, also called effective, back up to peak, we got to multiply it by a bigger number, 1.414, to get it back up there. To go from the peak back down, we got to multiply it by a smaller number, so that's 707. Yeah.
So just going back on the power, the E would be your max voltage, or would that be?
Well, honestly, this peak right here, it could have been E for voltage or I for current.
Okay.
Does not matter, because it's still a sinusoidal wave, and the application still applies.
So you would use that peak for
Peak
the
is
power.
peak.
Okay.
So if I'm measuring peak voltage, then it's voltage. If it's amperage, it's amperage. And
I think, let me know if I'm wrong. I think he's asking, when it comes to finding power, do we use peak or do we use?
oh, okay. That's a good question. So if I said, what is the power? To not be wrong,
Do both.
specify.
Okay.
Power effective, power peak. So that's how I would answer the question.
Okay. Thank you. Thanks, Chad.
Yeah, good translation.
Because I was curious about that too.
Yeah, that's a really good question.
If I ever see you on an airplane, Jack, I'm gonna yell, "Hi, Jack."
Only if you're going to Terminal C4.
Just for the record, I have no part of this conversation that they were just having. My name is Kevin Gehring. I do not approve. Okay, let's talk about some circuits. So if we have an AC resistive circuit, and remember, we're talking about 3 types of circuits. And so that is actually going to come out in this manner. So we can have a resistive circuit. We can have an inductive circuit. Or we could have a capacitive. And then we combine them. So we have an RCL, which is, it has resistors, capacitors, and inductors. Or we could have like an RC or an RL, or we can have, I guess, a CL or any combination of it.
CLR.
CLR, yes. It's how you clean stuff, right? It's just how you put the stuff in order. Okay, but talking about a purely resistive circuit so that we can kind of get going on this. Let me see. So an AC resistive circuit is not what I wanted to do. Pen, enter. There, okay. Is a circuit that contains only resistors. So is an AC circuit that contains only resistors. And Ohm's law is applicable. That's not what I wanted to write. APPLICABLE. That's not going to come out right. Hey, it did. Applicable just like with DC. Just like with DC. Just like with DC. All right, so we're good with that. So, let me think. Around the room. So, I don't know why I wasted the time doing this, but so R total equals what?
R1.
R1 plus R2.
1 over R1 plus 1 over R2, all that at 1 over. Yeah, okay, I see what I did. I went through some examples. We had 110 volt RMS AC power supplying 2 parallel resistors, 10 ohms each. Well, it's just 1 over 10 plus 1 over 10 equals 1 over, and we get, all right, we know how to do that. I total, so I equals, come on.
I1 equals I2.
I total equals,
And parallel, oh, and then it's added.
what's the formula for Ohm's law for finding current?
E
E equals,
I over
I equals
E over R.
Oh, yeah.
E over R, and E equals, I was kind of hoping to be more interactive and everybody was like, oh, I know that one. You
thought
do
it
know
was a
this,
dumb
right?
question. We were like, oh, yeah, we've said this.
Okay. So everybody's good. We know that. Okay. In a purely resistive circuit, volts and amps are in phase. I did it again, damn it. Somebody's just going to have to yell, change man.
I don't mind the old one.
Really?
I was
Tony
always-
was already complaining about it.
I was
So
always-
is it nicer this way?
I think it will be when you're used to it.
How long have you been doing it this way?
Like a week.
Okay.
Yeah.
Feels like it's been a lot longer. So.
I was always able to read your handwriting.
It is a lot harder. In a purely resistive circuit, volts and amps are in phase. In a purely resistive circuit, volts and amps are in phase. Me too, even as soon as I wrote it. I feel like I'm going to take it. All right, purely resistive. Volts and amps are in phase. So if we had to figure out the phase angle, it is 0. We're fine. Let's see, when voltage reverses, amps reverse. And every step in time, volts are doing the same thing as amps, but at a different
Phase.
amplitude.
Yeah.
Because volts are usually more than amps, right?
Yes.
Okay, changing pen. So if my volts are doing this, my amps are doing
A little below.
A little less.
little less. So they're both going to cross 0 at the same time, 0 at the same time. They're both going to peak at the same time because they are in
Phase.
phase, except the amplitude is different, meaning that the red line is higher, which is more. So we had more volts than we do amps, which tends to make sense. Changing pen. Maybe if I verbalize it. Okay. Let me see. Same thing. The power consumed by the circuit is the same. So power equals unchanging pen. I'm just running out of room here. So P, in this one I have P equals E RMS times I, what do you think is going to be? RMS. Okay, very good. And then for some reason I thought it'd be fun to do some sort of practice, which you don't need to do. Let me see. Just to drive home the fact that nothing has changed, but if you believe me, nothing has changed and nothing has changed. Let me see. So if I had a 110 volt power supply, and I had, it would look something like this. Neat, professional, logbook quality. This is 10 ohms, this is 10 ohms, and this is 110 volts. Then it's nothing more than EIR, and EI and R, just like we were used to looking at. And so how can we solve for that?
Transfer the voltage all the way across.
Sure, transfer the voltage all the way across because nothing has changed. 110 volts, 110 volts. Now what?
Solve for total resistance.
Total resistance. 10 1 over X plus
5.
10 1 over X equals 1 over X, which is 5 ohms. Then we solve for current. What is my current?
110
1 E divided by
110 divided by 5 is
22.
22 amps.
110
That 22 amps is going to split up evenly across here, or 110 divided by 10 is going to be 11 amps. 11 amps. All right. What is the power consumed with this?
110 on each resistor. Oh, sorry.
power total would be like
1210 on each resistor. 1210, 1210.
So the
I got
total power would be 2,420 watts.
2,000, because it is 110 times 22 equals 2,420 watts. Everybody followed? Because I feel like we kind of went back to almost 309 right there. The only difference is we added a funky looking symbol. Otherwise, this is 309 stuff, right?
little mustache.
Okay, little mustache. Little,
I don't understand the squiggle.
yeah. What's up, man?
It's the wrong kind of squiggle.
Okay, let's take it one step further. What is the I max? What is the I max in that scenario? It's on your formula sheet.
31.1.
Okay, I hear 31.1. So what we're going to do is we're going to take the I max equals
31.1.
the RMS times, so the RMS is how much?
22.
22 amps, that's RMS, times,
1.14.
because it's got to go more now. So 1.414, that's the standard, equals 31.1 amps. There we go. All right. And we can do the same thing with what is E max. And that was 110 times 1.414 equals 155.54 volts. Everybody's following me so far? Awesome. All right, shifting gears.
So our power max would be.
Oh, yeah, we could do power max too, but I don't know if that's a thing. All right, that pin right there. And I want 9 period space.
Wouldn't you have to know power max for a resistor? Like how much that resistor could.
Yeah, you have to know the size of the resistor.
Right, so you couldn't go off RMS. You'd have to, or would it not really matter if the resistor is only good for?
Well, okay, if we think about going back to what is the equivalent, it's the heat range. So
Right.
RMS would be same as the heat, which is what we're worried about. So that'd be the power I'd want.
Right.
So I would do RMS. Okay, before we move on to the next part of this, we're going to talk about magnetic fields. Because without understanding magnetic fields, we don't understand the next part. So magnetic fields. No relation to Sally. Again, very old guy joke.
Too bad.
All right, magnetic field in a wire. I'm very wordy, trying to cut down some words. Okay, so we have a conductor. And in a conductor, when we have current flowing, that conductor has a magnetic field that grows around it. Visuals, it's a wire there. Don't say I don't have visuals. So even when we played with this on a DC battery, whatever, when current flows through it, we have a magnetic field grows around it. Well, with DC, it grows and it just stays. And then we shut it off, it collapses. All right, so turn it on, it grows, turn it off, it collapses. And we talked about the fact that to create electricity, we need 3 things. We have to have a magnetic field, coil of wire, and relative motion. If we don't have those things, then we don't have anything. Okay. So if we take a coil of wire and we twist it, and now we've got a coil. So where have we messed with coils so far in lab?
Relays.
Solenoids and relays. All right, so it's nothing more than basically something like this, a whole bunch of wire, and plug it into a voltage source. Current flows through that, it creates a magnet and pulls some contacts down, right? Okay, so it creates the magnet, boom, electromagnet is what it is, and it's just there. And if I put another wire next to that, not this, but your thing, the solenoid, believe it or not, when you first turned on the solenoid and it turned on and the magnetic field grew, if I had something right next to it, it would induce a voltage into what is next to it. Because we have 3 things. We have a magnet that just got turned on. We have
Magnetic field.
movement of the so we have magnetic field. We have movement. What's the movement?
Oh, the growth of it is a movement.
Growth is movement. That's a major part of what we're going to study from here on out.
That's how the transformer, like you were saying earlier, the collapsing and growing pushes stuff through the sheet of paper, for lack of a better term.
Okay? Yeah. So, all right. So I turn on the coil. We're using DC, battery. Turn on the coil, and the coil turns on. Magnetic fields come across another wire sitting next to it, and as it grows, it will induce a voltage right here. But then it goes away. Why did it go away? What did we lose?
The movement.
The whatchamacallit, the
We
the
lost,
force, the
whatchamacallit is correct. We lost movement. We had one movement across it, and then it was dead. I mean, the magnetic force is still there, but the movement has gone. Now, when we shut off the solenoid, what happens?
A little bit more.
Movement.
Magnetic and movement. We'll get another piece of voltage out of this. All right, let's take a break.
That's why AC on and off multiple cycles.
I thought you were talking about how like with